And now moving on into our third installment from this chapter. Uh, as mentioned, we need to talk about how we go from sensation to perception. This is the final arrow in that diagram of seeing a tree that I had up earlier. So we have a section here on bottom-up processing, and we will talk about what works, what doesn't work here. And then we will have a section on top-down processing, which, as I said, I'll plan to put in a separate video to break this up. Okay, starting with bottom-up processing here. So the analogy in the previous video is like you're building a house, right? You're going to put bricks down on the ground, put bricks on top of bricks, and you're going from the ground up, from the bottom up. And then when you're done, you've constructed something, right? And so that's what bottom-up processing is from this perceptual view here, except instead of bricks, we're going to have sensations. And again, we'll stick with visual sensations because it's convenient. Brightness and color values building up to create a perceptual whole in this case, right? So, but there's a little bit more to say about bottom-up processing than simply just this stacking of sensations to construct something here. One of the things that distinguishes bottom-up from top-down is that top-down um, it is essentially relies on other knowledge and other information besides what's given to the senses, whereas a bottom-up process is sometimes described as a data-driven process, right? That is, it's just given the data. Is there a way that we can use an analogy to this building a house thing here? Maybe there's something here. So for example, let's switch from bricks to clay, right? So what happens with clay is, well, what's important here is that bricks are made of clay in some cases, right? So what we can do is say that what I'm going to do is I'm going to take these pieces of clay and I'm going to form them into some sort of unit, like a brick or something like that, and then I'm going to start stacking them together and see what I get, right? So make a house of some kind, has a shape and so forth. But on the other hand, clay is malleable. So one thing that I could do is I could just have a great big block of clay, and then I could take a form, right? What's a form? A form is a mold, right? That has a shape kind of embedded into it. And then I'm going to press this mold down onto my lump of clay, and I'm going to leave it sit there for the clay to harden, and then I'll pull the mold off, and then there's going to be a shape left over, right? So now I have imposed this form onto the raw lump of clay, right? So I didn't let the clay form the shape itself just by stacking it up and seeing what I get, but rather I imposed a shape on it. I molded it and manipulated it to to take on a particular shape that I want it to, right? That's top-down processing, but we're not there yet. So for bottom-up processing, we're not going to have such of an imposition, right? What does that mean from a psychological perspective, this imposition of a pattern or an assumption of a pattern? Well, that might mean something like prior expectations, right? So if I have prior expectations and experience or innate knowledge or any other thing that exists before the sensations have been received from our eyes and our ears, uh, then I might use those prior expectations to impose that kind of structure onto the sensations. But that's top down, right? So for bottom up, we're going to see if we can succeed in uh, constructing a perceptual whole from the sensations without such experience and expectation and other kinds of top-down assumptions, right? So that's our first question. Is it even possible to do this? Is it possible to extract and build a pattern from the sensory data without having assumptions, right? Without imposing a pattern? The way I've written it here is a little different, though. It says to extract a pattern from the gray level array without searching through a set of possibilities known in advance. What am I talking about here? Well, um, these are called templates, right? And So what is a template theory? So I'm going to jump ahead a little bit here. I don't know that we I don't really have a good depiction of a template in here a little bit. I could talk about it with top-down processing, but um, let me run it back to here to where we were, jumping all around. Here you're going to get the full McConnell classroom experience with me jumping around in the slides a little bit here. Uh, so what is a template? First, what's a gray level array? So this is what this is here. So let's say we're looking at something. In this case, I've changed it from a tree to a cup. It's easier to draw here. Uh, so what happens is that we have the distal stimulus. We then talk about the idea of light reflecting from the distal stimulus to the eye. Or if we want to use the digital camera analogy, it's going to work very well here. We're going to call this gray level array, right? And so that means is that we've created in the digital camera some pixels, right? And pixels have code and values associated with them, and that's going to be then the gray levels. But those then get encoded literally as data, right? And so that means that we can convert this into numbers. And so we can use numbers, and this will be an actual spatial 2 by 2 array of numbers here. We're going to have numbers going across in rows and numbers going down in columns, right? That creates an array in computer science, literally an array of numbers. And we can give them values like zeros and ones. We might want more than that if we want nuance. We might want more numbers to represent variations and shades of gray as opposed to just black and white. But here it's just black and white, zero for black, white for one, um, coding in light intensity, right? And then somehow I have to extract from this gray level array this information about brightness values in this two-dimensional array um, that there's a cup, right? And so it's that last arrow I'm talking about going from sensation to perception. And here I have this little notation, right? Question mark, exclamation mark. What the heck is going on, right? How does this work? Um, and it seems to be a semi-miraculous process that we could make this work, right? So back to the previous slide here. So we want to extract a pattern from the gray level array, but without having to search through a set of possibilities known in advance. So what am I trying to suggest here? Well, let's just say, for example, that I have already stored in some sort of long-term memory system a bunch of different gray level arrays of the type that I just had on the screen, right? And what I could do here is I could say that if this particular, I could have how many different kinds of possibilities and combinations do we have here? This is in fact just a 4 by 4, 16 different values. How many different possibilities are there? Well, we have to consult combinatorics and permutations here. We could compute that. I'm not going to bother with that. But of course, when it comes to human vision, we have literally millions of rods and cones in the eye, and therefore the amount of pixels we have is a pretty large number for visual processing. So how many possibilities do we have there? It's a lot, right? Um, so I could store all of the possible combinations though, right? And if I had that access, right, if I had this kind of stored long-term memory of all the possible gray level arrays that my eyes could potentially ever be exposed to, I could have them saved in long-term memory along with labels, right? And each one of these labels would be, here's a set of gray level arrays that corresponds to dogs. And here's a set of gray level array that corresponds to cats. And here's another set that corresponds to coffee mugs and another set that corresponds to trees. And we would have millions, if not billions and trillions of these kinds of gray level array images stored in long-term memory, and every one of them has a label associated with it. So then when I am looking at, in this case, as I have over here, a coffee cup, this is going to activate a gray level array in my current visual system. And then what happens is that I'm going to take that current set of visual sensations and I'm going to compare it to the billions or trillions of gray level arrays that have already been stored in my long-term memory. And I'm going to keep searching through all of those until I find the one that matches. And then once I match it, I can say, it's a cup now. because I have matched it to the appropriate pattern that's already stored in my visual memory. That means cup, right? So that's one way to think about how perception might work here, but that's not bottom-up processing, because what's happening here is that in order to recognize the cup, I have to have a stored form of data inside that's already in me that's going to play an important role in the recognition process. I'm essentially taking the bottom-up sensory data, comparing it to the already inside of us top-down knowledge of what cups look like, and I'm matching them up to see if they match. And that is what we sometimes call template matching, where the variations in possible things, like what kinds of patterns we might expect there to be if I'm looking at a cup. Um, well, I'm going to compare that to the current sensations, and if they do in fact align, then I know I'm looking at a cup. If they don't align, then I must be looking at something else. This turns out to be a computational problem that's not very appealing, because if I really have billions and trillions of these kinds of stored gray level array templates, then does that mean that I actually would have to sort through billions or trillions of these and make these kinds of comparisons one at a time? How long would that take? Our brains can process information very fast, but even acknowledging that, it's not quite clear that this process would take a reasonable amount of time. It could take a very long amount of time. If we asked a computer to do it, even the fastest computer in the world would take potentially longer than there is time left in the universe before it would ever calculate an answer to this. Assuming brains can be a little more efficient at doing this, it would be faster than that, but still not clear that it would be done in a reasonable amount of time. So that kind of template matching is not really a satisfactory way to explain how perception works, because we know perception is effectively instantaneous. You look at the cup, you say there's a cup, right? It's immediate. So we're doing something else here. We're going to have to find information in our gray level array without imposing the structure from a template. One possibility is called a feature analysis or feature detections process. Those might be called mini templates, and we'll talk more about feature detection a little bit later here, but let's first start with a major issue. So again, we have our diagram of how this whole process is going to work. We encode the sensations as values in an array of numbers, and I have to do something with this array of numbers that is not about template matching, that's going to tell me that this array of numbers means cup. So how could this work? What's it going to be? Well, one possibility is the whole perceptron model. And when we talked about artificial neural networks, we said, okay, that's one possibility. So what happens is that there's a whole bunch of different input values in the input layer, and that would be the actual numbers in the array. Some of those inputs are important, and some of those inputs are not important when it comes to what makes a cup in the image. So there's going to be a weight associated with each one of the input values. Then we're going to run this through our summation and activation function. And we're going to generate an output that says yes, cup, not, or no, not a cup. But then, of course, this system needs to learn. So then the idea is that we'll train it, and those weights get calculated and recalculated until the system starts to function correctly. And I had suggested this when we covered perceptrons in the first chapter. I think first chapter, maybe that was the second chapter. The idea of maybe this is how perceptual learning works in childhood, is that we get feedback and training. Well, there is one concern that this is how it works, because what we see with children is called one trial learning, or fast mapping, which is the very first time you tell them a new name for something, like that's a dog and that's a cup, they don't start to get it wrong again and again, and you have to give them continuous feedback over numerous repetitions until they finally figure it out. Instead, you just say that's a cup, and then from that point on, they just know cups, right? They don't require continuous correction. They're not perfect. They might make some mistakes here and there, but generally speaking, they learn words very, very quickly and start recognizing and categorizing the world as they are taught very quickly, learning words at a rapid rate from their, say, first birthday to second and third birthday. So this is an appealing option, but maybe only to a limited degree, right? Now, here's another possibility, right? I think I showed you this one before as well, the idea of having cells in the visual cortex that detect lines of a specific orientation called simple cells, and then there are also complex cells that detect lines of a specific orientation that are also moving in a particular direction, and then also the hypercomplex or end-stopped cells that detect lines of a preferred orientation, but that also stop within a specific range of the visual field so that there's a kind of a length limit on them, right? So we might consider these to be what we could call feature detectors. And so then the argument is that if we say that, okay, we have convincing, compelling neuroscience data here that says that the brain, the visual areas of the brain, primary visual cortex, contains these cells that detect features, then maybe what we can do is start defining objects by the presence or absence of specific features. So if our feature detectors are returning values here of true, this feature is present, then we could imagine how if an object is defined by a certain subset of all of the possible visual features that are out there, that recognition works in this way through this kind of feature analysis is what it's called. We analyze the visual scene for the presence or absence of features and then map whatever features we find to objects that are defined by a feature list, right? So like, oh, this object should have these features. A coffee cup should have certain features. A dog is going to have different features. And whichever ones we encounter for a given visual scene, which is determined by the activity of these cells in primary visual cortex, then that would give us recognition. I think I showed you this image before of an artificial neural network that instantiates this kind of activity of these neurons. And again, it suggests that we could explain from a neural network perspective how recognition could work through this kind of feature analysis. Here's an older way to think about it, but to me, I kind of like the simplicity of this diagram. It really captures what we mean by the concept of feature processing. So what we have here now, this is called the pandemonium model because of the use of so-called demons. Selfridge is just being a little literary here. So he's obviously not meaning that there are real demons in the brain or anything like that. So we're looking at something, in this case, it's the letter R. So we'll use this to explain letter recognition. So not trees or cups, but now letters. There's a challenge with letter recognition because letters can come in variations, right? We have all these various fonts and there's handwriting, which is highly variable. But the idea is that we could have an idea of something like this idealized letter R. We'll call it the exemplar R, right? Sort of a quote unquote perfect R. The ideal R as we think of it in our mind, right? And it has certain features. It's got some vertical lines. It has a diagonal line. It has a semicircular curve. The curve itself also has some horizontal components to it there. And so what's going to happen is that each one of these feature daemons could be something like a simple cell that detects the presence of itself, right? So there's a vertical line detecting daemon will check a box and say, okay, I see one vertical line. The horizontal line detector daemon might say, okay, I see two of those, right? And the oblique line, diagonal line, the daemon's going to detect itself as well. There's some right angles there, so maybe we have a right angle detecting daemon, and so on and so forth. And we're going to do that. And what we can now imagine is that these feature daemons are sending either excitatory or inhibitory signals to the cognitive daemons, right? And so some cognitive daemons have some of these features, like the one that corresponds to the letter B or the D or the P, and the R, of course, right? So there's varying levels of excitation across the cognitive daemons. Some of the daemons really have a very different set of features. So maybe like the letter V and W and X, they're receiving largely inhibition from these feature daemons. So they're unhappy, right? So the next question is, who's the happiest, right? Who's the one that's the most excited, literally, because it's getting the most excitations from the features? Well, it's the job of the decision daemon to kind of make that comparison and figure it out. And so then the decision daemon finally says, yep, that's an R, right? That's how this process is meant to work, right? And so this is just a, cartoon visualization of something that is kind of like a neural network. I've mentioned David Marr a few times in this course and the importance of his contribution to visual neuroscience. We're going to talk about that here as well, because here's another way that we might be able to think about how we can find edges in the visual scene and then use that to build up into a kind of a bottom-up recognition of an object. So once again, we're going to create a gray level array. This time we've done something a bit more simplistic. We have a checkerboard pattern, and we've encoded it into a gray level array with numbers, zeros for the black areas and fives for the lighter areas, right? That would leave open room for, say, values 1, 2, 3, 4, which could represent shades of gray, but because it's just a high contrast black and white checkerboard, we've got zeros and fives. And you can map it out here, right? You can see the black square maps to that array of zeros in the top left of the spatial array here. So I have a code, right? A bunch of numbers. And one thing we can ask is, how does the visual system recognize that this is a checkerboard pattern? Well, one way is to just extract the locations of these edges and be able to try to map out their locations to show that they all line up in consistent places. So let's imagine how we might do this. Let's start with the row number 1, right at the top. If you can see my mouse cursor, we're going 0, 0, 0, and then it goes 5, 5, 5. Wait a minute. The boundary between the 0 and the 5, that might prove to be crucial. So how do I find this boundary between the 0 and the 5? Well, one thing is we can do a simple difference test, right? That is subtraction. And so if I do, if I take pixel value 1 and pixel value 2, and I say, okay, what is pixel value 2 minus pixel value 1? Well, that's 0 and 0, right? So the difference between those two pixels is 0. And then if I do 0 minus 0, moving from pixel 2 to pixel 3, again, their difference is 0. But if I then do what's the difference between pixel 4 and pixel 3, the difference is 5, right? And then when I move through the fives, again, the differences are 0. 5 minus 5 is 0. But over here, I do 0 minus 5 and I get negative 5. So I end up with another difference here. So anytime that difference is non-zero, that means that there's a change in brightness between this part of the scene and another part. And that's when we can start to just perform this simple little routine mathematical operation to calculate the location of edges and contrast points in the visual scene. Now, here's a way of graphing it, right? So what I've done is I've made a graph. This graph is a function of our pixel values, which is x, right? And so again, we just map zeros across here. We map fives across here. So it steps up and then it steps back down. We get zeros here. Now, I described this before as a simple subtractive kind of process, looking for differences, but that's not technically what Marr did. What Marr did was a different, more sophisticated mathematical way of finding differences called differentiation, right? So if you've had calculus, you know what a derivative is, and that's what we're doing here. We're taking the derivative of this function, and whenever there, one simple thing about derivatives, right? One is that a derivative is a way of finding the rate of change in some set of values, whether it's usually we talk about the derivative over time. So how does position change over time? That's called velocity. How does velocity change over time? That's called acceleration. So the first derivative of position is velocity. But we can also take rate of change over spatial locations instead of over time. So we'll use x here to refer to spatial position instead of t for time. And that's called a spatial derivative. And so the derivative gives us the rate of change over spatial position here. And that means that if something is not changing, the derivative is 0, right? So going back to our position and velocity example here, if something has a constant position, that means it's staying in one place over time. So its velocity is 0, right? So in this case, if we have a set of gray level values in the array that are constant, the derivative of that function at that location will be 0. And that's what we're looking at here. We're seeing the derivative of our first function here is going to be 0 wherever there is constancy in the image. But as soon as there's a change, that's going to cause the derivative to spike, right? And then it returns back to 0 all throughout the fives. And then once we get over to the section where it goes from 5 back to 0, we get another spike. And this then is again the non-zero derivative. Notice, of course, that the spikes are relatively here positive and negative, indicating the direction of the change going up and then down again, all right? For mathematical simplicity, what's useful here is to take a second derivative. And what the second derivative does is it causes those rates of change to always either to go positive and negative. Sometimes it goes positive first, and other times it goes negative first. But what's critical here is that there's always a change of sign, right? The second derivative function always either goes from positive to negative or negative to positive. That's called a zero crossing, right? When we shift sign from positive to negative or negative to positive, we're crossing the zero boundary, right? So by doing this second derivative across the array of numbers, all that we need to do now is count the number of zero crossings, right? And we will count 2, of course, right? And so if we count 2 zero crossings, we can then say there are 2 edges in this row of numbers, and then we're going to shift down to the next row of numbers and do this again, right? And then we'll shift down to the next row and do this again. And then maybe we'll shift and start doing it vertically, right? So we'll start measuring columns of numbers too. So we're going to sift through, I mean to say we're going to sift through this array, repeatedly performing the derivative process row by row and column by column so that we can map out the total number of edges as well as their relative locations as a function of x, right? The result of this kind of process was developed by Marr, and he was able to show that if I take like a standard photograph and apply this kind of edge processing analysis, this contrast detection analysis on it, what it does is it does in fact create a map. And this map is a map of the brightness changes or the contrast changes in the image. And he called this the raw primal sketch. And there's a few examples here. This is a picture from this kind of work in the top left. What we're seeing here is a statue, like a sculpture, right? It's like abstract art. I think that's in Philadelphia. I'm not sure. And we have 3 different raw primal sketches that are generated on this, right? We don't need to get into all of the little details about how sometimes this mapping contains lots of detail, like the one in the top right, and other times, like in the bottom right, it has very little detail. There are different ways of performing the process, and there's different purposes here. Here down at the bottom is a picture of a child, and so again on the left we see the raw primal sketch, the different locations of edges and contrast elements here, or in this photograph of Albert Einstein. Again, we have kind of like a blurry image that generates one kind of raw primal sketch and a more detailed image here. We filter it and blur it to different degrees. What's the blurring process supposed to give us here? The idea is that the raw primal sketch is just a bunch of lines, but what we want to do is we want to kind of turn that into a more whole picture. So maybe we can fill in the gaps a little bit, fill in the blanks, and turn it into a more complete picture and not just a bunch of disconnected lines and so forth, right? So that's the next question. What, in fact, do we do next with the image, right? We have the raw primal sketch, which is a map of the edges, the contrast elements in the scene, right? Whereas an outline drawing is we kind of see it there as well. And it's 2-dimensional, importantly, right? But the problem is that visual perception is a more complex 3-dimensional object that we recognize and see. So one of the arguments here is that we still need to turn the raw primal sketch into a complete 3-dimensional mental image. And unfortunately, Marr's theory falls a little short of this. Marr does have some things to say about it, but one of the things Marr invokes here are things like the Gestalt organizing principles And these are, so we're going to see are examples of top-down processes, and therefore, well, it seems that we might have to shift into some top-down theories. Now, one alternative is to look into neural networks, these kinds of more complex modern artificial neural networks. So ANN for artificial neural networks, CNN for convolutional neural networks, RNN for recursive neural networks. What these all are is that these are more modern deep learning algorithms that might be able to successfully learn how to recognize objects much better than the old perceptron model even, right? Much more complex and faster learning process here. But this attempt of creating these various neural networks as a way of understanding how human vision works is pretty limited. There's no guarantee that just because a neural network can learn how to reconstruct an image from data and perceive what's there, doesn't mean that what it does is an exact replication of what the human visual system does, right? It could just be another way to achieve the same endpoint, but it's not actually an explanation of human vision. There's also the concern of what's known as biological plausibility. When we have these kinds of theories that suggest that this is how visual perception works, we still need to say that we can link this artificial neural network to an actual biological neural network to show that the mechanisms and the principles and the processes all look the same. That's not always the case. So therefore, if we can't show that brains have organizations that have an organization that works in the same way, say, a convolutional neural network does, then there's no good claim to be made here that that's what the brain is. Also, there's other stuff happening in human development that artificial neural networks and computer vision systems don't have, right? This genetic business, right? We are born with some genetic abilities for vision and to form and develop eyeballs that work and visual systems that work. And of course, there's a unique kind of experiential process that happens in infancy and early childhood that simply is not the same in a literal way as training a neural network. So this ultimately is maybe going to fall short a little bit, right? So again, as noted, we will maybe need to look at top-down processing alternatives to explain vision and recognition and not rely on a strict bottom-up approach. And of course, that is where we will call it a day today. Okay.